Hello everyone, my name is Ellen. Welcome to my final presentation for CS 358. I will be presenting on OpenCilk by MIT, which is a parallel programming language. So just to begin with some intuition on why we need parallelization in the first place, I think this graph does a good job at displaying why that is. So you can see here the display of Moore's law, where transistors count keeps doubling every year. However, you can see down here that single thread performance is plateauing. So that means a single line of code can't execute any faster on one core. So since we can't make any one thread faster anymore, we have to divide work across multiple cores, and parallelization lets us do that. So we're able to split tasks into different cores so our code can run as quickly as possible on today's multi-core processors. Let's begin with an overview of what is OpenCilk and how can OpenCilk help us with this task of parallel performing on our multi-core processors. So OpenCilk is an open source software infrastructure for task parallel programming, which was built on top of a pre-existing open source compiler called LLVM. And it specifically facilitates the writing of fork join parallel programs. So everything basically hinges on these two functions, which is silk spawn and silk sync. Kind of hard to say, but what we have here is just a sequentially running program. Silk spawn is launched, these processes fork off, they do their own computations, and then we wait for them all to finish at silk sync, and then the program returns. Very simple, very similar to OpenMP. And in addition, it has these productivity tools such as a race condition detector and a scalability analyzer. And for a really brief history on how this programming language came to be, it started as an MIT project and then added C++ support. It was originally just for C. Intel acquired it and had it supported for a while, but then ended up dropping Silk Plus support in 2017. And in response, the community initiated OpenCilk as a fully open source continuation. And the 3.0 version of that was just released last month this year. So for a general overview on what these fork join parallel programs look like is you have silk spawn, which spawns a task, and then silk sync, which waits for that spawn call to finish before the function ends up returning. So that's just very basic what a fork join parallel program looks like. For a brief overview of what the general keywords of this language are, it's basically this. It's very few function calls in the whole library. Very simple, just because you're marking the areas where parallelization can occur. So the two bread and butter functions are silk spawn and silk sync, which basically indicates that a function may be spawned, and silk sync, which waits, which halts the processing of the function until all of the spawn children return, and then we'll return the function. Silk for loop indicates that all iterations of the loop are allowed to execute in parallel, and silk scope delineates a parallel region of the function where the runtime system will ensure that execution will continue past silk scope only after all functions are returned, and will wait if necessary.
So as I was researching this programming language, I was thinking, wow, this sounds super similar to OpenMP. So I think it's important to point out the differences. For a quick comparison, I think the main distinction to make is that OpenMP deals in parallel loop iterations, and it's inherently data-centric, whereas OpenCilk is task-centric and deals in tasks. So as you'll see for OpenMP, the bread and butter is pragma OMP parallel 4 in front of your loop that you're trying to parallelize. As opposed to in OpenCilk, it'll be silk spawn and silk sync, which is a lot like pragma OMP task, where you're assigning a specific task to a thread. Additionally, there's a bit of a difference in how it talks to the compiler. So OpenMP, the way that the compiler reads it is it outlines parallel loops to the compiler, but the code itself is a big black box. Using Taper, however, which is attached to the LLVM compiler that OpenCilk is built on, the detach, reattach, and sync instructions are all visible to the compiler with this intermediate representation that it uses. So it's able to optimize those code blocks a lot more, whereas that's all a black box to the OpenMP compiler. Additionally, there's a difference in how the scheduling works, where there's static and dynamic scheduling, where all that's doing in OpenMP is varying the chunk sizes given to each thread. Whereas in OpenCilk, they use a work stealing scheduler, which I'll dive into that more in the next slide. And ultimately, the reason that Intel ended up dropping support for Silk was that it didn't do enough to distinguish itself from OpenMP and other programs. And so I think that's what they're trying to move toward using this open source, OpenCilk project, where they're moving away from Silk and they're calling it OpenCilk, so it's all open source. So I do think OpenMP has added support for this scheduler, but this is specifically what OpenCilk is built upon, which is this idea of a work stealing scheduler. So for an example of this, let's look here. It's all formed on this idea of a double-ended queue. So you can append to the back or to the front of this. So the way that this works is that worker one just works down its queue like this. So it's starting on job one, then it'll go to job two, then it'll go to job three. Same thing as a regular queue. But what happens when a different thread becomes idle, like worker two, all the way up to worker P, is once it becomes idle, it can go to the end of this other worker's queue and steal it and start working on it. And so this is a way that it's able to more quickly get through all the jobs assigned and fork tasks as easily as it does.
So we can see the results here published in their paper of the speed up of OpenCilk against other parallel programming languages. So you can see here Strassen right here. That is the matrix multiply. So we're all familiar with that example. You can see that they're all performing around the same, but as we go down this line, the shape of the execution tree and the call tree gets highly irregular. So just for an example of quicksort, the way that quicksort works is that a pivot is chosen, and depending on what the pivot is, the two sides can be highly irregular. And so when those calls keep on happening and happening, the speed time, the runtime, and the speed up really goes down for OpenMP and this other one called 1TBB, but it stays up for OpenCilk. And why that is that Silk spawn is almost as cheap as a function call. So OpenMP has a much higher per task overhead. So launching a thread is a lot more work for OpenMP than just spawning something and adding it to the scheduler. And so what we see is that there's a lot of load balancing that's able to happen with this work stealing scheduler that we see in OpenCilk.
All right, I thought we'd start with the call tree for this Fibonacci function without any parallelization, so we can see how the execution model for OpenCilk divvies that all up. So let's start with Fibonacci of 5, something simple. So since n is not less than 2, we're going to return fib of n minus 1 and fib of n minus 2. So that'll become fib of 4 and fib of 3. So then following this down, since this one gets executed first, that becomes fib of 3 and fib of 2. And then we'll go even deeper into that recursive step. That becomes fib of 2 and fib of 1. And then fib of 2 becomes fib of 1 and fib of 0. And then we've reached the base case up here. So this becomes 1 and this becomes 0. This gets added up. This bubbles up to 1 here, and then this becomes 1. And then down here, same thing happens again. This becomes 1, this becomes 0. So all of this bubbles up, adding up to 3. And then we go back down here. So that's half of that recursive step done. This becomes fib of 2 and fib of 1. And we have the same step over here, 1 and 0. This is the base case of 1. This bubbles up to 2. We have 3 plus 2 equals 5. And so this is what the call tree looks like when just calling the function on one processor with one worker. That is how the function will execute. All right, now here we have the Silk code, which is parallelized. And so this task is embarrassingly parallel. So there's no information that needs to be shared between the processes. We can just split it up and work it out. So we're gonna walk through the call tree to see how OpenCilk handles this problem. So let's start again on worker 0, doing the same function, fib of 5. And so walking this through, it's not the base case, so we'll spawn the n minus 1 branch. So that'll spawn fib of 4 right here. And then compute n minus 2 in its current function. So that'll become fib of 3 right here. And then wait for the spawn child to finish. So that means it'll wait for this right here. And then combine results, so bringing those together. And that'll become it. So basically, to understand how this gets handled is worker 0 has what's called a double-ended queue. So to look at what that looks like over here, basically, fib 3 gets put right at the front, so that'll execute immediately. So right when it spawns this new one, fib 3 will be the first thing to get executed. And the spawned child gets put at the end of its queue. So fib of 4 gets put over here. And so what that means is that worker 1, which is sitting over here, is able to steal from the end of this double-ended queue. So it'll come over here, steal 4, and then start working on fib of 4 down here, doing the exact same thing that worker 0 did up here. And then that holds for worker 1, worker 2, and however deep the recursive step becomes. And so this is called a work stealing technique, where any idle thread is able to come grab work from the end of a different thread's processing queue. And so this is like a form of dynamic scheduling that makes it so you don't have idle threads sitting around the entire time. And then if worker 1 ends up finishing this, it'll move on to work on fib of 4, and then that won't be worker 1. But it really just depends on how long things take. So to continue this execution model, we have worker 1, which will run fib of 4, which will go to spawning the n-1 branch, which is fib of 3. So that spawns this in, and then that's 3. Then fib of 2 comes over here. And so again, the same thing happens where the double-ended queue of worker 1 gets fib of 2 put at the front, and then at the end of its queue, it gets fib of 3. So it'll immediately start working on fib of 2, and then fib of 3 is free to be stolen by another one. And then each time this is happening, they're each doing silk sync, so they're waiting for the child thread that they spawn to finish before they go and return, or they join and return. Then the same thing happens here. Fib of 3 spawns fib of 2. So now this would probably be worker 2 executing. Then we have fib of 1 over here, and this will just return 1. Again, same as the other one. Oops, this will return 1 and 0. Then fib of 2 returns 1 and 0. And anyways, you see how it works, where it's a double-ended queue, and workers pull from the end of the previous worker's queue in order to make the task scheduling much quicker. And then this will all bubble up. This will bubble up the same as last time from 3 to 2, and it'll return 5.
And finally, just to end with some limitations on the future of OpenCilk and what's going on with it, is there's not really a ton of widespread adoption of this programming language, and that's why Intel started removing support. It wasn't getting as adopted as they wanted it to be. Additionally, it doesn't work with GCC or unpatched Clang. And so this is a problem that I talk about more down here, but there's a lot of the performance gains that you get with OpenCilk are because of the LLVM and taper compiler that it uses, but it needs that compiler to be able to run. So there's kind of a toolchain dependency where it's not able to get those performance gains running on another compiler. And finally, there's no reduction that you see within OpenMP, where you're able to point that toward a variable and it's able to handle the data sharing that occurs between threads. And that's not developed, that's not ready to be used in OpenCilk. So that's another limitation of why this isn't being adopted and used as commonly as something like OpenMP. And here are my references. Thank you for watching.